All right, everyone, we're back to our usual location. We will see whether I can get the lighting to work. Probably not, because I never can. Hopefully the board does not fall down. I make no guarantees, because I just had to reattach it. So we're going to see what happens. Anyway, what I want to start talking about today is a new type of topic. Well, it seems kind of new. I mean, it's not totally new, but the topic we're going to be looking at, apart from whether or not the board is actually going to remain in place, is going to be the topic of antiderivatives. So we spent much of the semester talking about derivatives. We started the semester talking about limits and continuity, but then we pretty quickly got into derivatives, and we spent pretty much the rest of our time talking about derivatives, how you find them, what you can do with them. Now we want to talk about sort of the opposite of a derivative. So there are two questions that I want to specifically answer for you today. First of all, what is an antiderivative? And secondly, why do we care? Like, what good are they? The answer to the second question is actually going to be, they're good for a lot of things. And in fact, we're not even going to see everything they're good for today. But I will explain to you at least one of their major uses and why we are so interested in them. So first of all, what are they? We will say that capital F of X is an antiderivative, which I'm going to be abbreviating as AD because I am not writing the entire word antiderivative 50 times today. We will say that capital F of X is an antiderivative for little f of x if the derivative of capital F is equal to little f. Yay, there we go. So the antiderivative is simply some function whose derivative is whatever we started with, okay? And in this sense, it is very much the opposite of a derivative. So examples. X squared is an antiderivative for 2x. Because if you take the derivative of x squared, you would get 2x. So is x squared minus 3. Because if you took the derivative of x squared minus 3, you would also get 2x. Some other examples here that we could come up with, we can say, well, maybe sine x is an antiderivative for cosine x, okay, right? The derivative of cosine x, the derivative of sine x is cosine x, so this is an antiderivative for cosine x. So is sine of x plus 2, though. In fact, you will notice there's sort of this pattern here, right? Where I'm giving you an antiderivative and then pointing out, well, I could add a constant to it. Well, that's true in general, right? If capital F of X is an antiderivative for little f of x, then so is capital F of X plus K for any constant K. And the reason for this, it's sort of not anything really that tricky or anything when you think about it. The reason for this is simply because if I take the derivative of a constant, it's 0. And so the derivative of capital F of X plus K is equal to the derivative of capital F of X. But if capital F is an antiderivative for little f, then this is still just equal to little f of x, okay? So, one of the kind of strange things that you got to get used to with antiderivatives, they are not unique. In fact, you can always add a constant to them, and you will get another antiderivative. So, one of our questions is, just how non-unique is an antiderivative? How many different antiderivatives do we have? And the answer is pretty straightforward in the sense that, well, it's not straightforward at all, but in the sense that we've seen the answer before in a slightly different context. So we already know the answer to this question. We just may not be aware that we know it. So remember that if f and g are differentiable on some connected interval a to b, and f prime of x equals g prime of x on this interval from a to b, one of the things that we proved, and we proved this by using the mean value theorem, one of the things that we proved is that f of x minus g of x is equal to some constant on the open interval a to b, or on this connected interval. So one of the things that we can say then about antiderivatives is that it follows that if capital F1 of x and capital F2 of x are antiderivatives for the same function little f of x on an open interval from a to b, then f1 of x equals f2 of x plus k on this interval from a to b for some constant k. Now, I don't know what that constant is. The constant could be anything. It's really easy to see the constant could be anything because the derivative of any constant is 0. But that's the worst that could happen, is that our two different antiderivatives differ by a constant on this interval. Now, some people kind of are sloppy about this, and they will tell you, oh, two antiderivatives differ by a constant. That's not quite true. It's almost true. It's not quite true. So we do need to be a little bit careful. The reason we need to be careful is because maybe the domain of our function is not going to be just one interval or a connected interval. So here is the sort of situation that I want you to be careful about. Consider f of x equals 1 over x. Then capital F of x equals log of x is an antiderivative. Log absolute value x, I should say, sorry. Is an antiderivative for 1 over x. But so is f1 of x, which is going to be the piecewise defined function, log of x plus 1 for x bigger than 0, and log absolute value of x minus 1, whoops, I put a minus x, I meant minus 1, when x is negative. So the thing is that on different intervals, I have a different constant going on here. So we have different constants on different intervals in the domain. Okay, but that's the only thing that can go wrong. So if I have this function and it is a derivative of some other function, then the only choices that I can make essentially are on each interval that comprises one connected piece of the domain, I can choose a different constant. But on each one of those intervals, the constant has to be an actual constant. It can't be different numbers at different points. So, for this reason, what we can say is that on a single connected interval of the domain, the antiderivative is unique up to adding a constant. So just one constant per interval is the point. Now, this is why a lot of people will just say, oh, the antiderivative is determined up to a constant. The reason that they say that is because in many instances, we're dealing with a function whose domain is maybe all real numbers. And so there is only one interval and thus only one possible choice of constant. But in other contexts, we might be dealing with a function whose domain consists of several different intervals. And they'll still just say, well, the antiderivative is determined up to a constant. What they really mean is that if you pick a single interval of the domain and restrict your attention to that one interval, then the antiderivative is determined up to a constant. There is a good reason why we are usually only interested in one interval like that. And we will see as we go through a little later, we will see why we are often only interested in one interval. So for most practical purposes, what people tend to say is what my advisor used to call morally correct. It's not really morally correct, but what he would mean by this is that it is correct for most practical purposes. The antiderivative is determined up to adding a constant. Strictly speaking, that is on each particular interval in the domain. So different intervals in the domain can get different constants. But in practice, we are almost always only interested in one interval at a time, and thus we can say just one constant and that's it. Now, if you think about it for a minute, every derivative that I know gives rise to some kind of an antiderivative. So, for example, we can say that if our function f of x, and then we list our antiderivative capital F of x, if I have x to the n, the antiderivative of this is going to be x to the n plus 1 divided by n plus 1, and then plus a constant, provided that n is not equal to minus 1. N equals minus 1 is sort of the special case. That's because, that's the weird case with derivatives. So for x to the minus 1, then our antiderivative becomes log absolute value of x. Now you'll notice I'm just writing log absolute value of x plus a constant. That's because, strictly speaking, I'm going to just write the antiderivatives on one interval. And if you want the most general form of the antiderivative, then you have to do a separate constant for each interval. But like I said, we are usually going to only be interested in finding the antiderivative on one interval at a time. And therefore, we are only interested in having one constant. Plus, otherwise, you have to start making a whole mess of constants in here. So usually when people write the antiderivatives, they either drop the constant entirely and leave it implied, or they just write one constant and leave it at that. So I'm going to follow the same convention. Thus, this is strictly only true on a single interval at a time, but yeah, we're not, like I said, it's rare that you ever have to deal with multiple intervals. If you do need to deal with multiple intervals, it's very easy. You just deal with multiple constants, one for each interval. But, chances of having to do that are pretty minimal. So these are some examples. We've also got a bunch of other examples. For instance, if I start with the function e to the x, well, the antiderivative for that is going to be e to the x plus some constant. If I have, we already did cosine of x. That has an antiderivative of sine x plus a constant. What about sine x? Well, the antiderivative for that would be negative cosine x plus a constant. In fact, you can come up with an entire chart, which I am not going to make on this whiteboard. If you look in chapter 4.9 of your textbook, they give you an entire chart of 18 different antiderivatives that we know. And they each follow from derivatives that we know. If I know the derivative of a function, then I can take that derivative and the original function is an antiderivative for it. So every derivative that we know gives me an antiderivative. And like I said, I'm not going to list every single one of them out here. Look it up in the table in your book. There's no point in me writing the whole thing out here again. Now, why do we care about antiderivatives? Well, the reason we care about antiderivatives is kind of because of the same reason we care about derivatives themselves, in a sense, right? Derivatives these are actually rates of change. At least that was our idea for them, right? When we came up with the idea of the derivative, we were really looking for what is the rate at which this quantity is changing with respect to some other quantity. So, for example, the velocity v of t is supposed to be the derivative with respect to time of the position x of t. It is the rate at which the position is changing. Now, our initial interest was to say, well, we can now calculate the velocity as the derivative of position. That's great and all, but here's the thing. What if instead we know the velocity and we want to be able to talk about what is the position? Well, in that case, we need to be able to use an antiderivative. So, for example, let me suppose here, just to give you a really kind of fairly straightforward example to think about to begin with, given that the velocity as a function of time is equal to, let's say that it is equal to 10t, let's suppose that we want to find the position as a function of time. Well, the answer is that x of t is an antiderivative for v of t. So all I need to do is to find an antiderivative here. And the answer then is that x of t is going to be equal to 10t. What am I even saying here? I'm so sorry. Not 10t. It's going to be equal to 10t squared over 2 plus some constant k. So this is going to become 5t squared plus a constant k. Now, you'll notice here that there is a constant involved. And we probably don't like that because we probably want to find the position as an actual function, a well-defined or completely defined function. We do not want to have some random constant floating around in our answer, most likely. But here's the problem. It has to be there unless we have more information. Because without more information, I can't tell you which particular antiderivative we're interested in this problem. It could be any of them. Okay, so what is this constant? What is k here? Well, the answer is actually something that we can notice pretty easily. See, if I plug in t equals 0 into x here, I would get 5 times 0 squared plus k, which is equal to k. So k is actually the position at a time t equals 0. I'm so sorry, this lighting is this terrible situation, but fortunately in most positions it seems like the lighting's okay. It's just, I'm really sorry about the glare. So you may have to pause the video at a few points to make sure you can copy things down without a glare. So what is going on here? Well, this constant is what we call an initial condition, because what it's telling me is the position when t is equal to 0. And the initial condition, in other words, it's telling me that when t is 0, this is what my position is. Well, that means that if I have a problem where I give you the velocity and I also give you an initial position, you can find the position uniquely. This is not really surprising. Think about sort of intuitively what's going on here. If I just tell you the velocity, you obviously cannot tell me the position in general because you don't know where you started at. All you know is how your position changed over time. So it makes sense that we would be able to figure out how much the position changed given the velocity, but we would not expect to be able to find the position itself unless we also know where we begin. So really, this is not like all that surprising when you think about it. Intuitively, this is kind of what you would expect. So here's an example of using these types of initial conditions. So let's suppose that we modify the original problem and say where the starting location is -20. Well, in this case, then what we know is that x of t is going to be 5t squared plus k, and we know x of 0 equals -20. So if I plug in 5 times 0 squared plus k equals -20, it gives me k equals -20, and that gives me my function x of t is going to be equal to 5t squared minus 20. So there we go. We figured out our answer. And we've gotten a unique position here. Now, by the way, this is an example of something, a more general phenomenon, because what we are really dealing with here is something called a differential equation. A differential equation is like a standard equation, except in the equations you're used to dealing with, our variable, our unknown quantity, is a number. In a differential equation, the unknown quantity is a function. Not just a number, it is a function. And instead of just writing the function and some relationships with the function, we also include derivatives of the function. So in this case, what we're really saying is that the derivative of x of t is equal to 10t. And this is an example of a differential equation. It's a fairly basic differential equation, but it is in fact a differential equation. One of the things that often happens when you're dealing with differential equations is you find that there's not just one solution, or even just like a finite number of solutions. So when you solve an algebra equation, the variable usually comes out to where you get just one solution, or maybe you get a family of solutions, but there's usually just a few of them or whatever, right? Like think about solving a quadratic equation. You can get 0 solutions, 1 solution, or 2 solutions. With these differential equations, what generally ends up happening is you get a family of solutions with different constants. So you actually will end up with an infinite collection of solutions for your equation. It's kind of interesting that way. And this is an example of that, where there are many different possible x of t's that satisfy this equation. Because in fact, I could change this -20 to anything else, and we get a whole infinite family of possible x of t's. To decide which one we have, we need some additional condition. Now, I want to notice here, the condition that's given, it doesn't have to be the initial condition necessarily. So here is another example of one of these types of things. Let's say that this time we are given that the velocity as a function of time is equal to negative 4t. And after 3 seconds, we will assume here t is measured in seconds, the position is 6. And we want to find x of t in general. Well, the answer here is that x of t is going to equal negative 4t squared over 2, which is, plus a constant, which is, of course, just negative 2t squared plus k. The other thing that we know is that x of 3 should be equal to 6. That means negative 2 times 3 squared plus k should be equal to 6. So what is this going to give me? This is going to give me negative 18 plus k equals 6. And that gives me k is equal to 24. So we end up with x of t is equal to negative 2t squared plus 24. Now, this is not an initial condition because it does, like strictly speaking, an initial condition tells you the conditions when t equals 0 or when your independent variable is equal to 0. In this case, I didn't give an initial condition, I gave a different kind of condition. But the same kind of reasoning applies. It allows us to find what is this function in general. Now, sometimes we can get things that are even more complicated. For instance, instead of just giving you the derivative, I could give you the second derivative. So as an example of this, where this really does come up rather frequently, let's suppose we are given that the acceleration as a function of t is equal to, let's say, minus 3 times the sine of pi times t. And we are also given that the velocity when t is equal to 0 is equal to 0, and the position at t equals 0 is going to be equal to, actually, let's say that the velocity at t equals 0 is equal to 3, and then we will say that the position at t equals 0 is equal to 0. I think that will actually, let's make this 3 over pi. I think that will work out nicely. And we want to find the velocity and x of t as functions of time. Now, the way we're going to do this is the same as the previous example, because the velocity, well, acceleration is the rate of change of velocity. So using the same techniques as the previous example, I can find v of t. And then I can use the initial condition to find the constant. Once I have v of t, I can use the fact that v of t is the derivative of x of t and do the same argument. So it's really the same problem as we just did, just done over twice. So what I'd like you to do is take a minute, pause the video, and see what you can say about this problem. See if you can solve this problem. It is trickier in some ways than the previous ones, but I think you might be able to handle it. Okay, so were you able to get anywhere? Let's see what we can write down. So, v of t is going to, in general, be equal to 3 over pi cosine pi t. And the reason we know that it's the 3 over pi is because if you take the derivative of cosine pi t, you pick up a factor of pi. So that's where this pi comes from. And then we have to say that it is plus a constant, which we usually call v0, although sometimes it's called other things. So you can call the constant whatever you want to. And then what we can say is that v of 0 is equal to 3 over pi, which is equal to 3 over pi times the cosine pi times 0 plus v0. If you solve this, this becomes 1, and so this gives me v0 equals 0. So technically v0 in this case does not represent the velocity at t equals 0. Sorry about that. I had to adjust something really quick. Instead, it's just some constant. But we end up with this being equal to 0. So what we get is that v of t is going to be 3 over pi cosine pi t. And the constant in this case actually just comes out to be 0. So then we're going to solve for x of t. And so we're going to say that x of t is going to be 3 over pi squared sine pi t plus some constant x0. And when I plug in x of 0 is equal to 0, which should be 3 over pi squared sine of pi times 0 plus x0, I get that x0 is equal to 0 as well. And so this constant of integration is also 0. That means that x of t is going to equal 3 over pi squared sine pi t. Now, this was a little bit of a trickier problem because we had to deal with this pi. And we haven't fully talked about how to deal with those pi's. In this case, maybe it's not too hard to see what happens. But in general, we're going to see that there is a rule for dealing with what happens when you have those constant factors in there. However, hopefully it's not too difficult to see that, yeah, this really does just pick up an extra factor of pi in the denominator, because when we take the derivative, we'd end up multiplying by a pi. And then we were able to use these initial conditions to get these functions. It turns out that actually this kind of situation is a real kind of situation. So this actually describes what is known in physics as harmonic motion. Harmonic motion turns out to be one of the most important things in physics. The place where you usually start encountering it is when you're dealing with some sort of a mass bouncing around on the end of a spring. However, it turns out that that's not the only place where harmonic motion happens. It turns out that harmonic motion actually underlies just about everything in the world, because everything in the world is made up of quantum fields. And although you have to quantize things in order to, do the quantum part of it, it turns out that those fields classically kind of obey harmonic motion. So what you end up with is you can sort of think of, you end up describing everything in the world as sort of these harmonic motion fields, not just single masses moving around on a spring, but this infinite field of harmonic oscillators and things like this. So yeah, it turns out that this is really important, but this is one example of it. Now, where else does this kind of thing happen? Because I've given you mostly examples with physics here. Well, you can come up with other types of examples as well. For instance, let's say that our investments obey the condition that the derivative of the investments with respect to time is equal to, let's say, 1/10 e to the t. And we want to know if our initial investment was $1,000, find I of t. Well, the answer is that I of t is going to be an antiderivative here. So it's going to be 1/10 e to the t plus some sort of a constant. And then we're going to say, well, I of 0 is equal to 1/10 e to the 0 plus k, but it's also equal to $1,000. So this means that k is going to equal 1,000 minus 1/10. Which is equal to 9999 divided by 10. You could also think of this as just 999.9. So this is going to become 1/10 e to the t plus 999.9. So that's going to be our investment value at any given time. And you can think of other situations too as well. And really, any place where you could talk about rates of change and then you need to recover the actual quantity, you're going to be talking about doing an antiderivative sort of situation, okay? Because the rate of change is the derivative. And so if I give you the derivative, I'm really giving you the rate of change. Now, there are other applications for antiderivatives as well. And they're pretty closely related to this, though. Because here's the thing. We would expect, if we are given the rate of change, if you sort of add up all the rates of change, then you would kind of expect that that should give you the total change. Or to put it another way, normally, if I want to say what is the total change, I can add up all the little pieces of change in the middle. Now, what is a little piece of change? Well, at any given time, we know our rate of change. And so over a small enough time interval where the rate of change is approximately constant, we can say the change over that time interval is our rate of change multiplied by the width of that time interval, or the length of time interval. If you add up all of those little changes, you should get the total change. And so, in some sense, we expect that antiderivatives should kind of be telling us something about the total change. So let's write down intuitively what we just said. Suppose that R of t is equal to the rate of change of some x of t. I don't know why I'm calling it x, but we need something. So we have x of t. Then, if R of t were a piecewise constant, in other words, if it were constant on, like if we could break up the domain into intervals and on each interval it were constant, the change over each piece would be R evaluated on that piece, which I'm going to call Ti star, times the width of that piece. So times the width of that, or well, let's actually, instead of TA and TB, we'll just call it B minus A, where R is constant on B minus A, and Ti star is a point in the interval from A to B. And since R is constant, it doesn't matter what point I pick. But the other thing that we would notice is that the total change would be expected to be the change in x. In other words, if we look at the two endpoints, the full endpoints, not just one interval, but if we look at the total change in x, in some sense, that should just come from adding up the changes over each piece. Now, even if the rate of change is not constant, we would sort of expect this to be the case. So what we sort of want to say is that if the rate of change is given by r of t, we kind of expect the total change to be simply the change in x. However, what we know is that x of t is an antiderivative for r of t. So, what we would kind of expect is that you might be able to find the total change in something by finding the antiderivative and then finding what is the difference in the antiderivative between the final point and the initial point. And this does not depend upon the constant that we choose. Why doesn't it depend on the constant? Well, because as long as we're dealing with just one interval with one constant, then the difference, the constants are going to cancel, right? If I have the same constant added to the function at both ends and I take their difference, the two constants just cancel each other out. And so we don't really have to worry about the constant, okay? As a result, we sort of have this expectation that if you know the rate of change, you should be able to find the total change by looking for an antiderivative. And this leads us into something called the fundamental theorem of calculus. Now, this is not something we are going to finish off today. I'm just mentioning this here. The fundamental theorem of calculus essentially says what we just said is true. The total change can be calculated by looking at an antiderivative of the rate of change. So in some sense, total change is an antiderivative of rate of change. Now, intuitively, that is almost obvious. Maybe my explanation didn't make a lot of sense, but if you think about what's going on, the rate of change is a derivative. The total change is just a difference. So the total change should be an antiderivative of the rate of change. That is sort of like what you would expect. Now, what we're going to do, and not today, because we're almost done here. This has gone on long enough for today, I think. But what we're going to do is we're going to talk about a couple of different things. First of all, we're going to talk about some properties that we would expect total change to have. And then we're going to talk about how you could make those ideas precise, but also how these properties allow us to prove the fundamental theorem of calculus. We will also talk about how you actually phrase the fundamental theorem of calculus, because this is a very imprecise, intuitive way of understanding it. But we'll give a precise statement of it. We will prove it by using certain properties that we expect to have happen. And then we will also talk about how you make those ideas precise. Because the interesting thing is, historically, the fundamental theorem of calculus was proved by basically, Newton was able to prove the fundamental theorem, but he did it by using these properties that he just sort of said, yeah, we can define something, we can define the total change, and it will have these properties. Well, the problem is that he didn't give a precise definition for total change. It wasn't until later with a guy named Riemann that we had a precise definition for this total change. Now, it turned out to be fine because the properties Newton's wanted to use have to be true of any reasonable definition, and they are true of Riemann's definition, because Riemann's definition is a reasonable one. But the fact remains that Newton did not quite prove that what he was working with existed. And that's the sort of thing that physicists don't tend to worry about and mathematicians do. We mathematicians are always worried about whether what we're talking about is well defined and whether it really makes sense. Physicists like Newton are less concerned about that. They're usually willing to just say, presumably such and such a thing exists, and we can talk about its properties. Anyway, we will see how you prove this, what properties you need to prove this, and then we will also see how you can give a precise definition as well. And that's what we're going to spend a bunch of time talking about this week, and then we'll talk about how all of this, how we can use the antiderivatives for these applications.